Welcome to the DSA series. In case you're wondering what you're doing here, I'm sure you're interested in DSA, data structure and algorithms, which is why I've stumbled upon this video. In case you're wondering who I am, my name is Kallol Bhattacharya, and I have been in the IT industry for the past 24 years, recently retired. And I thought that my knowledge in the IT industry is best put to use if I am with you and I'm trying to impart whatever I have learned in terms of these lecture series. DSA, Data Structure and Algorithm, is going to be an exciting series, and we will cover everything from the basics of DSA to the advanced concepts of DSA. We will cover a plethora of questions that are typically asked in the university curriculum. So anybody who is interested in DSA as a topic, as a subject, anybody who has DSA in their university curriculums, they can definitely benefit out of this. Be with me. I'm sure this is going to be an exciting journey in order to prove how and what modern algorithms can do. Thank you so much.
Hello, welcome back, and we are back with one of the very important data structure, which is linked list, and it's used in various places. It's used in various applications. We'll see a couple of them today, but then this typically starts off a fresh module as far as your syllabus might be concerned, and we would be talking about linked list and trees in this module. Today's lecture will cover a single linked list, and we will cover all kinds of operations that are there. We will cover the algorithms that are relevant to those operations, and we'll also cover the complexities. And lastly, what we'll do is we'll also cover the applications, as I said, how to use linked list in order to create something which is which we have already done during our array days. So we did arrays, and we used arrays to create stacks. We did arrays to create queues. So we will now use linked list to actually create stacks and queues, which is a very important application of linked list. So that's what we will try to achieve. And this particular session might be a bit longer. So you please feel free to probably pause, browse, skip whatever you want in order to be pinpointed in terms of exact topics that might be interesting for you. So if we start off with the linked list as a topic, and if we start off by understanding why we at all need a linked list, right? So there are so many data structures. You have learned about arrays, you have learned about stacks, you have learned about queues. Stacks and queues we have implemented using our standard arrays. Then why linked list, right? So let's try to understand that problem first. So what we are trying to now do is, let us imagine that we have to create a variable x where we will put the value of 4, and what you see here is actually nothing but the memory map. This is how in memory it might look, right? It's a very simplified form of representation of memory, where each block is actually one byte of space, right? So with that in mind, if each block is 1 byte of space, and I have to allocate x equal to 4, how many bytes do we need? Natural compilers will have 4 bytes allocated for an int, right? So I have to find out contiguous 4 bytes of space in this memory. Now what are the blues and what are the yellows? These are already taken, right? These are already used memory, right? I cannot take this from here. The free memory are actually the yellow blocks. Now, if I actually say that x equal to 4, then the first place that I get x and I can allocate x is here, these 4 blocks. These are contiguous 4 blocks where I can allocate for x and give it some memory. That is the 4 bytes that it needs. So let us say that we have taken this block and we have utilized this block, and this block has also become a blue block, right? Now let's say that now I want to create an array, right? And for that matter, let us say that I want to create an array called A of size 3. How many bytes should I be allocating here? I should be allocating 12 bytes of space, right? 3 integers multiplied by 4 bytes per integer. You know about it. It's going to be 12 bytes. Where do I get 12 contiguous? Remember, arrays are contiguous. You had learnt about this in C, right? So now where do you get 3 bytes or 3 blocks of 4 bytes each, contiguous element, right? You will get it here. If you see here you are going to get the next set of 3 bytes. Here it will not be able to give you 12 bytes of space, right? Here you will not get 12 bytes of space. Here you will not get 12 bytes of space. Here you will get 12 bytes of space. So this is the area where you will get the 12 bytes of space. So let us start allocating that 12 bytes. So this is 1 byte, 2 byte, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these 12 bytes get allocated for you, and internally this is the first pocket of the array, this is the second pocket of the array, and this is the third pocket of the array. Internally these are the pockets of the array that you would have recognized. So this is also done for you. So this also we could allocate. So this we could do, this we could do. Now imagine that I am giving you the next task to give me an integer array. An integer array, let's call this integer array now as B, and this B I want 10 bytes or 10 pockets rather, not 10 bytes. So which will be equivalent to some 40 bytes of space, right? So this will be equivalent to some 40 bytes of space. Now do we have 40 bytes of space, right? So let's see if we have 40 bytes of space. Now wherever you go, right, wherever you go, I want, what is this? We are trying to define an array. The array means that it has to have 40 bytes of space. Just by looking at this you can say there are no contiguous elements which are free that has 40 bytes of space, right? So this doesn't have 40 bytes of space, this is not 40 bytes, this is not 40 bytes, and that's it. The rest of the things are small. So there is a wastage of memory, as you can see. Probably if we counted all these yellow blocks together, maybe we would have got 40 bytes of space, right? But we are unable to do that for an array because array needs contiguous memory blocks, right? So what we will do is we will say that can we allocate 4 bytes of space, that is one integer, and then can we utilize the next block as another 4 bytes of space. However, they need not be contiguous and they will be stitched together with a link, right? Can we do that? Let's see. So do I have the first area where we have the 4 bytes of space is this. So we will take this as 4 bytes of space. So this is one pocket of the array. So we did one pocket of the array, right? Next we are going to search for 4 bytes of space, and these 4 bytes must be contiguous because 4 bytes is necessary to hold an integer, right? At least the integer portion is contiguous needed. The rest of the portions which is stitching 2, 3, 4, 5, 6 integers can go on in non-contiguous blocks. That's the assumption. So can we say that once we have allocated this 4 bytes of space, we have another situation where we can allocate this 4 bytes of space, right? So then we have created a 2 integer areas where we can store integers. Then we have this byte of space. So we have created 3 integer areas now. We have these 4 bytes of space. So we have created 4 integer positions now. Again, we have these 4 bytes of space. So we have created 5 more, right? And then we have this 4 bytes of space, right? So we have right now created, we were at 5, so we are now at 6, and we have this one also, which is 4 bytes of space. We have 7. Let me count it just to make sure I'm going correct. 1, 2, 3, 4, 5, 6, 7. I'm correct. And by the way, this should be not 4 bytes. This should be 40 bytes of space, right? So we were asking for 40 bytes of space, and we were not getting it. That is why we said, okay, let's see if we can get individual 40 bytes with 4 blocks at a time. Need not be contiguous. That's what we are trying to figure out. We got 7 of them. We can't get here 4, so we will take these 4, right? And then we got some 8, and then we will take these 4. We got some 9, and then we will take these 4. We got 10. So that's what we wanted. We wanted 10 pockets, and we got 10 pockets. 10 pockets are there. This is effective utilization of memory, right? So what we need is all these 10 should be grouped together, right? They cannot be just siloed elements in the memory, then they become just variables. They have to be grouped together, they have to be stitched together, just like an array, right? But not in a contiguous form. So can we create something which will point, can we create something which now starts pointing from the first block to the next block, and from the next block to the next block, and from the next block to the next block, and from this 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 block to the next block, and from the last next block to this block. So what we did is, from the blocks, we somehow, let's say, connected them together, right? Then if somebody starts from this block, right, then he can actually navigate through these connections. He can navigate using these connections and get to this element, and again navigate using this connection to this element, and what he's simulating is what we got in arrays, right? Everything is grouped together. One block knows the next block knows the next block, and so on and so forth, and the last block says my next block is null, I don't have any next block. This is what we achieved in terms of a linked list, right? And that's what is a linked list. It effectively utilizes the memory. So what all it achieves? It is dynamic in nature. If I want to add one more block, I can add one more block. I can remove a block by just removing these links. So I can say that I don't want this link. Then what happens is this element gets automatically removed because it is not linked with this element, right? So this stops here. This block stops here. Because there is no link here, this element is removed. So it is dynamic. We can reduce the elements, we can increase the elements, and of course we discussed that it is a non-contiguous, right? And we need to make sequential access, because from here, as I explained, if we start, we have to go to this next block, we cannot jump to this block, right? It has to be sequential access, and that's why we say that it is a sequential access. Next, insertion deletion is very fast here, because if I have to insert here, what do? I will do this. If I have to insert something here, right, somewhere I will find a node. Let's say this is my extended memory map. Let us assume this is my extended memory map, right? And let us assume that there are 4 blocks of space here. Now I have to insert an element, and I want to insert this element here. So let's say whatever I will keep here will be inserted in place here, right? If I keep this, if I want to insert this block here, right? When I say insert this block, we are not inserting it in that particular memory position. We are saying that, Mr. Memory, you should start pointing from here to this block, right? That's all we are saying. So what we'll do is, we will remove this link, right? And we will create a link from this block to this block, right? And from this block, we will create a link to this block. And that creates the connection. So now if we go, we will start from here, go here. From here, we see that we have to go here. From here, we see that we have to go back. And from here, we have to go here. From here, we go to the next block, and so on and so forth. And that's where we see that insertion becomes so easy. Now imagine if you had to do it for an array, then what would have happened? You would have to have created the space for that array at that position, moved all the elements to the right using an order of n algorithm, and then put the value there. So that's the advantage of using linked list, both for insertion and deletion. It is going to be fast because the order is not going to be order of n. Now, efficient, of course it is efficient. It is making utilizing all the space that is available, but it's going to be complex because we'll have to work with pointer arithmetic, right? So that's what the introduction of linked list is, and I hope you can understand the need for the linked list and what all advantages it brings to the table. Now, if that is understandable, then of course this is something that we have already discussed. This typically comes in terms of when we talk about linked list. Why linked list? There was array. Why linked list? Right? So that's the answer here. I told you it is dynamic. We discussed about it. It is non-contiguous. The size is actually dynamic here. It can grow or shrink in size. Sequential access we have discussed. It is fast we have discussed. Efficient we have discussed. Complex we have discussed. And traversal is using array index. Here we'll use the next pointer. The pointer, the lines that I drew, we'll use those. right? So that's what we will do there. And access time complexity is order of 1, this is order of n, in the sense that if we have to access a particular element, then that element can be accessed directly by an address in array, but that element cannot be accessed by an array the index. We will have to go around the linked list from the start till we reach that, and we will show that in some of the algorithms that are coming forward. So with this, if I start the actual of how we represent a linked list, right? So what we are talking about is we are talking about that I need some placeholder to store data, right? So we are saying that I need a placeholder to store some data. So let's say that I need a placeholder to store some data, and let's say that this is of integer type, right? So this is a data portion that needs to be available to us, and I am saying that along with this data, I also need a variable or a placeholder that can store the address of the next node, right? When I say the address of the next node, we are talking about this link, right? So this link is what we are talking about, address of the next node. So this is the link we are talking about. So this is my data, and this is the address of the next node. These are the two variables we will need. That is pretty much understandable, I hope, right? So we are saying that we will store these two. So if we have to store the address of if we have to store these two, and these two should be grouped together, these two should be grouped together to create one variable, one single variable, right? So we need to create one single variable that in turn has two more variables, and hence we are talking about what? Structures, right? So this is a structure of what? Of what we call it as node, right? So we will call this particular block as a node, which contains two things, standard two things, data, that is the payload, and a next pointer, right? And this next pointer, why is it a pointer? Because it is storing the address of the next node. Address is stored inside pointer, so it has to be a pointer. Now where is the next node? The next node is here. Let's say the next node is here, and in this next node, what will happen? You will still again have some data for that node, and it will still again have some pointer for the next node's address, right? So it will have some data here and the next node's address, right? So this, if this address is 1000 for this particular block, then this next node will be pointing to 1000, right? And this next node might not be pointing to anything, which is perfectly fine. And if we keep some data here, right, then this becomes our linked list, because now we have this node pointing to the next node and the next node pointing to null, which means we have two elements now in our linked list, and we need actually a head pointer additionally, so that we know that this first node, let's say, starts from 500 as an address, right? Let's say the first node starts from 500 as an address, so we need a head pointer which will in turn have 500 as an address, so that it starts pointing here, right? When it starts pointing here, and if we know the head address, we know the value of this head, right, then we can enter into this particular address, get the data from here, right, print it, go to the next pointer, see that there is one more address where it needs to go, print the data, go to the next pointer, and stop. And that's how we will traverse through a linked list that we just now created, right? So I hope you understand we need multiple variables inside one aggregated group, which is a structure. So we are creating a structure called node. Those multiple variables are in data, and the next data is basically a structure type of data, right? So it's the same data pointing to what? It's pointing to what? What is this? This is a node. What is node? A struct. So struct node, and we have a pointer, start next, right? So that's how this is coming. And what is this? This is pointing where? This is also pointing to a node. And what is node? It's a struct node star head, and we are putting it null to start off with, right? I hope you can understand and appreciate this fact. And if we start now instead of this detailed view, if we now start talking about a bit of abbreviated view so that we can I can show you something more around it, then we will typically draw a linked list like this. We will say that let's assume 4 nodes, right? So let's say that we have one node here, we have one node here, we have one node here, right? And let us say that this is our next pointer, this is our next pointer, and this is our next pointer. Let us say our data is 75, 77, 9. Let us say this is at 1000, this is at 2000, and this is at 3000. Therefore, this, if it has to point here, then it has to store 2000 as the address, it has to store 3000 as the address if it has to point here, and this has to store null because this is the last element in the queue. And definitely we need a head which will need to point to the first element, which is in this case 1000. So this points here. So if we now start with this, so if we know this, then we can traverse here, print this, go here, print this, go here, print this, and then stop. When I say print this, I mean any kind of operations that you want to do. So that's how a typical linked list works. And in order to do this, we have to do these operations. We may have to sometimes insert a node here, right, which is called as insert at beginning. So somewhere here we might need to have a node like this, right? So we have to insert a node there. How it behaves we will see. I will explain all of this as we go forward with each of these algorithms. But for now, let's assume that each of these functionalities will do something with this linked list. Insert at beginning will insert at the beginning. So this 1000 will not point, this head will not point to 1000, head will point to a new node. Insert at end, something here will be getting added, right? That is insert at end. Insert at a position, so I say second position, then something here will be added at the second position. Delete from beginning, that means this one will be deleted. Delete from end means this node will be deleted. Delete value, if I search for 77 and delete, this value will be deleted, or this node will be deleted. Traverse the list, we have already discussed, we are traversing like this. Search the list, if I search for 9, then it has to traverse and say that 9 is found here, right? So those are the functions, those are the operations that we will right now discuss. Okay, so now if we say insert at beginning, right, that's the first operation we will start discussing. Now let us say that we have a linked list and we have head which is basically pointing to nothing, right? So head is pointing to nothing. There is nothing in the linked list. So insert at beginning, because head points to the beginning of the array. So insert at beginning means that let's say we will have we will start inserting 9, let's say, as a data value to the first node, right? So that then 9 will get created here where head will point, right? So head will point to a node which contains 9. And when we next want to insert, let's say 77, then we are talking about insert at beginning. So 77 should come before 9, right? So what will happen is we need to change this and say that now it should look like this 77, which is then going to go into 9. And then if we say that I want to insert at beginning 75, then what is going to happen? We will have to change this and say that head will now go into 75, 77 and 9, and 9 will go nowhere rather, and that's the linked list that we'll try to build, right? Okay, so to do that, what we'll try to therefore do is remember that this is insert at beginning, right? So what we have done is we first inserted the first element and it got pushed to the right, as the next element came in and the next element came in, this became the rightmost of the last element. And in this same order we'll have to probably insert. So we will be inserting 9, then we'll insert 77, and then we'll insert 75, and we'll see how this entire thing works for us, right? So if we now start inserting 9, then we will utilize this value as 9, right? And once this value goes in, what we are saying is, we are saying that malloc, please step in and give me, what is malloc? Memory alloc. I'm sure you know from your C days that this allocates what? This allocates a structure node kind of a memory size, right? Size of structure node, because our structure node represents the node that we are trying to build, and the node has to be created in memory. So we are trying to create a node in memory which will have, let me put it in this way. So we are trying to create a node in memory, right? And this node will have two sections, one for the data and one for the next pointer, right? We know that node has been already defined earlier. Assume that we have asked malloc that give me a memory that can store node. It gave us a memory. This is the memory it gave us. Let us say that this memory is given to us at a location of 1000, right? And inside that and this memory, when it actually creates, it gives us with a return of a void pointer. And we are saying no, I don't need void pointer. I need to cast it into a node pointer so that I can create a variable called new node and store this 1000 there, so that it now starts pointing to that node pointer. With a void pointer, I could not have assigned it into a struct node star pointer because it is a node star pointer. I need to cast it to a node star. Malloc returns void star, right? So that's where we will say that, okay, I will define a node pointer. I will define a new node pointer. This new node pointer will have 1000 and this will point here. That is what happens in this line, right? And then we say new node, wherever you are pointing, the data block, this is the data block and this is the next block. I hope you remember that, right? So this data block and next block, I am going to say that new node, please fill up the data block, go to 1000 and please fill up the data block with the data of 9, right? And new node, so this is done, and new node, your next has to be the head. Where is head? We started off with a blank list. Remember, we started off with a blank list here, right? So where is head? Head was here. Head was here, and this head was having null, right? So this head, because it was a blank list, head was having null. Head is the most important element of a linked list. With head, you can navigate the linked list. You can do anything with the linked list. The only thing that you need is head, and that's why we will have to be very cautious about head. Head at the beginning will be null, and that's what we are saying, that we will assign the new nodes next to be null. And that is perfectly feasible or perfectly applicable, because when 9 is inserted, then 9 is the only element. Next element of 9 is null, and that's why it is null. Then why we had to push it to head? We could have directly written null, right? We had to write it as head. That's because we will understand it when we insert the next element. Just stay with me. So new node next is equal to head. I hope you can understand that new node next is head here. Because new node points here, that next is this, and that becomes equal to my head. Now head equal to new node is the last statement. Now head equal to new node means what? Head equal to new node. New node is 1000. So head will therefore no more contain null. Head will therefore no more contain null. It will contain 1000, because my new node contains 1000. So I can safely now, because this particular bracket is getting encountered, and struct new node, this one was a local variable for this, right? This block, this element or this memory will go away. It's a local element, right? It's an auto element in as far as C is concerned, auto pointer element, and it will go away once the scope of this block is over. But I have tactfully stored this 1000 here, so I have no need for this variable anymore, and this 1000 therefore now starts pointing here, right? And this variable gets deleted, right? So that's where my function ends. So I have, if somebody now has head, he knows 1000, I have to go 1000, he goes, he gets 9, then he reaches null, he stops. Now I have to insert 77, right? If I have to insert 77, first line is what? First line is creating that blank memory. So let us create the blank memory here, right? If I create the blank memory here, let's assume this memory is at 2000. Now if this memory is at 2000, then that particular 2000 is getting stored where? Inside new node. New node is going to get declared again. So new node gets another memory. So new node now has 2000 here, and this again is a local variable inside that particular function scope. So this local variable gets created, this particular local variable gets created again, and this particular local variable now holds the address to the new node that we just now created. And then we say new node data equal to value. We were doing it for 77. And then we say new nodes next is equal to head. Where is head? Head is at 1000. Right? So that's where now this will contain 1000. As soon as this becomes 1000, this starts pointing to the next node. Right? And that's why you are pointing it to head, because you are that's why this null was done through head. So this 1000 is automatically going to come from head, and hence it is going to be inserted at the beginning. Before this 9, this will be inserted. Right? So that's the beauty of using it with head like this. And then that's not over. So which means that this is pointing to this. Then this particular line should cease to exist, because now head should point to the beginning, and my beginning has become 77. So head should start pointing to here. How will head point here? Head has to be equal to the new node. New node has 2000. So we will put 2000 inside new node, inside head. So head will be equal to new node. Head will become 2000, and hence head will start pointing here. So this is the second iteration. For the third iteration, if we insert 75, right, then 75 if we have to insert, I'll just make some space here. So let's make this connection like this, and let's make the new node now, which we create as 75 here. So we have created 75 here, and this 75 will be created through the same process. I'll not repeat that. So what we'll say is that this new node that got created with 3000 as an address, and therefore this new node variable that is here, this new node variable will have 3000, and now instead of this new node pointing to and by the way, this new node was pointing to 2000 in the earlier case, so we will now start pointing it to 3000 now because of this line. The new node's next is going to be equal to head. Right? So new node's next is going to be equal to my head, which is basically first of all, new node will become equal to the address that it gets. So the address it gets is 1000. So new node is 1000. New node is pointing to this, which is perfectly fine. Data I have already filled up, and new node's next is equal to head, which means head is 2000. So of course this should point here, right? And the way it will point here is that we'll say it is equal to head. Head is pointing to 2000. So this is no more valid. Right? So this is no more valid, means 2000, the head 2000 is no more valid. If it is 2000, it will keep pointing here. So we will take 3000 from this new node and put it inside head. As soon as we do that, it points here. And then we don't have any need for this new node. The function will be over, and this new node will be gone, and this is the array that we just now create, or rather the linked list that we just now created using insert at beginning. Every time we create a new node, we will insert it at the beginning. We'll change the head to start pointing to that new node, and we'll push the new node, the previous new nodes to the right. That's what this particular insert at beginning operation tries to achieve. Now the complexity of this is pretty simple, because every time this is going to, there's no loop. This will just create a new node and just adjust the pointers. So the complexity of this is order of 1. Right? And the space complexity, again, it is in place, so it will be order of 1. Right? So this is about the first operation, which is insert at beginning. So if there is insert at beginning, then there is going to be an insert at end. Right? So insert at end, if we talk about insert at end, then we will build the same linked list that we have built. Right? So we will have head, which will be pointing to, let's say, 77. It will point to 75, it will point to 9 will point to nothing. Right? If we try to figure out that we are going to create this particular list, then in this list, what we are doing is, we are typically first element that we are adding is 77, and then we say insert at end. That means after 77, 75 will be added. Then we will add 9. Right? At the end, we are going to add the elements. So that's how we will proceed when we talk about insert at end. So the same set of steps. First, our head is basically pointing to null. So head will have null inside it. Okay, now if head has null, then I'm going into malloc and I'm saying that malloc, please give me a memory. Please give me a memory which is of size node, which is fine. So malloc will do what? Malloc will start giving me a memory. So malloc will say that, okay, I'm going to give you a memory of size node. You take it, it will have the data portion and it will have the next portion. And then malloc will say, I'm going to give you a void pointer. I will say I'll convert it in the same manner into a node pointer and I'll store it into new node. Right? So we will have a new node here, which will be a pointer variable, and this pointer variable will therefore start holding the address of this. Let's assume this as 1000. New node will start holding 1000, and inside this we will store 77. And how? Because this line gets triggered, new node data is equal to value and the new node's next is equal to null. This is a fresh node, so we will put new node's next is equal to null. Now we have to adjust our head to point to this particular new node. So if the list is empty, our head will have to come to the new node. So if the list is empty, that is head is equal to null, then we will say our new node our new node will therefore point to or our head rather will point to the new node, and new node is 1000. So now the head starts pointing here, because we said if head is equal to null, then head is equal to the new node, right? And that's where we will stop. It will return. It will return means there is no scope for this. This was a local variable. This gets destroyed. So now what we have achieved? We have achieved that we have a head which is pointing to 1000, and that 1000 contains 77 and null. And then we will say that I want to insert one more element 75. When I say one more element 75, malloc will come in and say I'm going to give you the area where you can store 75, like this. So I will say, fantastic, you have given me an area. That area is at 2000. I will store that value of 2000, that is the pointer, into this new node variable 2000, right? And I will store it here. So this 2000 is now pointing here, and there I will say go and do a data equal to value next equal to null, data equal to value 75 next is equal to null. So I will say do that, and then I have to create this link, right? I have to create this link. So how will I create this link? I will say my head is pointing where? My head is pointing to my head is pointing to 1000. So I will need to run a loop here, and why I'll just explain. This is the portion we are trying to capture now. Now I don't know whether this head is pointing to 1000 and after that there is some more elements before which we have to insert, or after which we have to insert this last element. Insert at end, right? There could be many such elements here. From head, if we go to 1000, 1000 might go to 1001, 1001 might go to 1002, and so on and so forth. There could be many such elements. Right now in this example, we have only one element at this particular iteration, but there could be many elements. So what we'll do is we will say, okay, now let's run our loop, right? We will say that we will create a temporary variable, or we will say that we have our pointer t, a temp pointer t, and that temp pointer we will always keep as head. Why? Because I'm going to change this temp pointer now. If I change head, then it will actually impact my entire linked list. As I said, head is the most important element. Don't play around with it, right? So we will take it inside temp and we'll play around with temp. So we'll say temp, you are actually head, which is fantastic. That is that. And then we'll say while temp arrow next is not equal to null. So but temp is pointing to 1000 and 1000 arrow next is null. So it will stop there, saying that this is the current last node and you have to insert after this. That's all this node tries to say. It picks up the current last node. Because the next is null, it is the last node, right? So that's where we will say that start t, you are going to go and keep on doing a next till you find the next as null. And it did that. It did that. While t arrow next not equal to null, this loop will not enter at all, and it will come out. So what is the value of t? Value of t is 1000. Then t's next should be what? The new node. So T's next should be new node, and that will establish this connection. So T's next will be the new node, right? So we will say T's next, you are new node is 2000. So T's next becomes new node, right? And then T is a local variable. This bracket is encountered means this is lost. So T is no more there. This variable is no more there. This link is no more there. I don't need this. This is gone. And so is new node gone. So what does this linked list look like now? It looks like 2 elements in the linked list, right? And it is perfectly valid 2 elements that you have right now. Right? 77 and 75, 1000 pointing to 77, 77 going into 2000, 2000 having 75, and then finally we have null, and that's what we have. Now we had the last element 77 to be 9 to be inserted. The last element is 9. So we are 9 now trying to insert 9. We'll call the same thing. Malloc will come into the picture. Malloc will say, I'm there to help you. So Malloc will allocate me what? Memory, and that memory we will put into where? New node. So Malloc says I have given you the memory at 3000. So I will typecast it into my new node pointer. So my new node pointer is looking like this, and new node pointer will have 3000. So new node is now pointing here, and I'll say new node, you now are pointing to 3000. Please go there and put what? Put the data as value. What is the value? 9. What is the next? Null. Okay, good. Now head is equal to null. No, my head is not equal to null in this case. Head has 1000. So then what happens is I have to make a T which will contain somehow this 2000. Why 2000? Because 2000 is my last node, right? And I have to change this null pointer so that it starts pointing here. So that's what we will do with this struct node start T. So for first thing we will make it as equal to head. So that's what we did here. We will make it equal to head. So now with head I will say, okay, node T arrow next not equal to null. Yes, it is pointing to here. Its next is not null. Its next is 2000. So what does it do? It will say that make T point to 2000, right? So instead of T pointing to 1000, take this next and place it inside T. So we will say that now T will become equal to T arrow next. So T will become equal to T arrow next. T arrow next has 2000, put it inside T. Now T is now pointing not here. T is not pointing here. Instead T has started to point where? T has started to point here, right? And T arrow next time it runs is null. So it comes out of the loop. Now T has 2000, and all we are saying is T arrow next is equal to new node. So T is 2000, arrow next is equal to new node. New node has 3000. So this now becomes 3000. This now becomes 3000. And as soon as this becomes 3000, this particular link gets established, right? And that's what your insert at n is all about. You are keeping on inserting a new node, and you are pushing or looping through your entire list and seeing what is your last node, and then adjusting the next to point to the new node. That's all you are doing. What is the time complexity? Because you have to go through this entire process of finding where is the last node, you can go so many steps, n steps, right? So therefore your time complexity will be order of n, and your space will be still order of 1. So that's going to be the time complexity for insert at end. Now if we move on to the next operation, which is insert at a particular position, right? So let us take this example, and I've put this example here, that we have a head pointing to 75, 75 pointing to 77, and then pointing to 9. Insert 15 at the position 3. In fact, this is a typo here. We will say insert 20. Insert 20 at position 3, then 20 gets inserted at position 3. How do we do this? Right? Again, it's going to be pretty simple. First, we'll have to build the list. Right? From a blank list, we'll have to build that list. Now, insert at position would mean that we will have to have insert at position accept a position and the value that needs to be inserted in that position, right? So we will therefore assume that that we have created a head, which what I'm trying to say is, I'm trying to assume this structure is already created, and that's what we are trying to replicate and change by inserting a node at position number 3, right? So let's assume that this structure is created. So if this structure is created, what will head contain and what will the others contain? So let us make placeholders. Let us put the elements here and then we will see. So we have 3 elements. We have 3 elements like this, right? And each of these elements, let's say, have an address. And each of these elements are rightfully pointing to their next elements. So this will have 1000, this will have 2000, and this will have null, right? So this will be pointing here, this will be pointing here. And what does this contain? It contains 75, this contains 77, and this contains 9. And this head, where is it pointing? It should be pointing here. So it should have 1000. So this is our current structure. Now we say insert at position 2 the value of 20. So what we have to do? Insert, right? We have to create a node. So we will take the help of our friend, which is malloc. So we will say malloc, please give us a node. Malloc will say happy to create a node for you. This is your node. And then we will place that new node's address, which is, let's say, 4000, into our favorite new node variable. So our favorite new node variable now has 4000, right? And then we'll say, new node, you are pointing here, please change the data. So we are saying, please change the data. So the data will be changed to what? The data will be changed to 20. We are inserting 20. And we will also say that if the position is equal to 1, right? We are not having position equal to 1. We'll come to this case a bit later. Let us finish the case that we have started. So till now, what we have done is we have created this node that we have kept here, which is this new node, and we don't know what to put here yet, and we don't know how to adjust this 4000, how to adjust the head, what we had done in the earlier example. So the rest of the code that we have here is going to talk about that. Let's talk about that now, and I hope it will be clear after this. So what we have is, we are saying that again, you can very well understand that we are trying to insert at a position which is going to be the 3rd position, right? We are trying to insert it here at the 3rd position. Now when we are trying to insert at the 3rd position, then this particular entire thing, where do you think we should stop? I mean, in the sense that I hope you have by now understood that in order to go to this 3rd position, we have to start from head, we have to move here, then we have to start from head, we have to move here, and then we have to move here. And because we traversed 2 positions, right, one here, we will have to stop here, because right now if we stop here, then only we can remove this 2000 and put 4000 there and take this and point it here. So those are the things we have to do. We have to stop here, we have to point it here instead of this, right? And then we have to point it back here. So these are the 2 things that we have to do. So where do we stop? We stop at the node previous to the insertion position, right? So we stop at the node previous to the insertion position means, first of all, we will take our favorite temp pointer, or T. In this case we have taken temp, so we will take a temp pointer here, which incidentally will point to the head. So our head is at 1000, and now because this is at 1000, it is pointing to the head, and then we will say that I want to start from I equal to 1, right? And why I equal to 1? Because at the position 1 we have a special case, so we'll come to that. So we don't want to touch 1. After 1, wherever it is, position 1, we will move on with that, right? So we have a position 3, so position minus 1 is going to be I equal to 1 is less than position minus 1, which is 2, right? And where is temp pointing? Temp is pointing to 1000. What is temp? Is temp null? no, then temp equal to temp arrow next, right? So I is less than 2, temp is pointing to a valid area, right? Temp is pointing to a valid area. By the way, this should be 2000, my bad, my apologies for that, this should be 2000. So temp is pointing to a valid area, and because temp is pointing to a valid area, therefore temp equal to temp arrow next will fire. If temp equal to temp arrow next fires, then this will become 2000, right? So now we are pointing here, so we are now pointing here, right? So this is now pointing here, and when the loop runs, I becomes plus plus. I hope you have noticed that I becomes plus plus. So now I has become 2, 2 is less than 2 is false. So because 2 is less than 2 is false, the loop will exit, right? This loop will exit. It will not check temp arrow not equal to temp not equal to null, because there is an AND condition, and this AND condition is already false. There is no point of checking this. So it will come out. When it comes out, what is the value of temp? 2000. So where is temp pointing? Temp is pointing here. So what do we need to do, right? We just need to say that temp, wherever you are pointing, that next needs to be pointing to the new node. Temp, wherever you are pointing, that next needs to point to the new nodes next, right? So what we are saying, that temp, wherever you are pointing, temp is pointing to 2000. That next means temp's next, right? In fact, we will adjust temps next a bit later. Let us keep it here for now, right? This is 3000. Temps next should point to 3000. If it was 2000 earlier, then that was again a typo from my side. Again, apologies for that. This should be 3000 as it points here. I'm sure you can understand these typos. By now, you should be understanding that the next points to the next address. Now, what I'm trying to get at is that if temp is coming out from the loop at having 2000, then we have positioned our temp here. So we have positioned our temp here. Now we are in a position to say that new node, wherever you are, your next becomes 3000. Why? Because we have temp. So temp arrow next is 3000. So new nodes next becomes 3000. So temp arrow next is new nodes next. So now this starts pointing here, right? And then we have to remove this. So how do we do that? Temp's next is this, right? So we are removing this and making it point here. So where is this 4000? New node. So we will say that our temp arrow next is equal to our new node, which is 4000. So now this starts pointing here. Our code ends here. If our code ends here, then this new node is gone. It's a local variable, gone. This link is gone, right? And the start temp is also gone. This I is also gone. So what do you have left with? You have left with this structure. Don't you think we inserted it at a position 2? Yes, we did. And if we were supposed to insert, let's say 99 at the position of 1, then what would have happened? So if position equal to 1, before that what has happened? A new node got created. A new node got created, right? And that new node's data got created with 99, and new node variable got created, which is a pointer, which started pointing to this, which let's say is at 5000, right? And when this is there and new node is now pointing to 5000, we are saying that position is equal to 1. If position is equal to 1, tell me what should happen. If position is 1, then I should be able to insert my new node next. I mean, what is actually going to happen is this particular element should be the first element. So head should point here and this should point here. And that's all we have to do. So what do we need to do then? We will just say that new node, your next will point to head, because head points here. So that creates this link. New node, your next points to head. So new node, your next points to head. And head, what you are going to do is, you are now not going to point to 2000. You are supposed to point to 5000. So please start pointing to 5000 by adjusting this. by adjusting head equal to new node. 5000 is in new node, so head becomes equal to new node, and that's what you did, and you returned. That's all. Right? So insertion at a particular position has to be handled in two different cases. At one, the logic is slightly different because you don't need to loop, and at any position the logic needs to loop to the last but one position, and from there you have to adjust the pointers. That's all there is to it. But the time complexity is going to be an order of n because you are doing a loop to position yourself at that position, and the space complexity will be order of 1. Right? So that's on the insert at position. Now let's come to some delete operations, right? So this is going to be simple enough for you to understand because we have gone through the loops now. And if we say that we had a head here, and I will not put the addresses now. If we say we have a head here and we have a head here, I mean we have an element here, we have an element here, and I want to delete from the beginning, right? I want to delete from the beginning means this should not be there. So what does that mean? That means that this should not be there. That means this should be pointing here, right? And that's all we have to do. We have to just shift the head. That's all we have to do. First of all, if head is equal to null, then the list is empty, so return. Otherwise, what we'll do is delete from beginning. Delete from beginning means I have to create a temp. First of all, I'll create a temp, and my temp will point to my head. Let's say head has 1000, so my temp will point to 1000, and my head arrow next, sorry, my head, this head particularly would be my head arrow next. That's what we did, right? Head arrow next. Head arrow next will be the new head. So that's what this is. Head arrow next is equal to new head. Right? So tell me one thing. What is this particular syntax doing? And why was this temp necessary? We are not looping anything here. Right? And this is very interesting to understand. Let me just step back a bit. So what we said is our head, which was pointing here, will now point here, and this link will cease to exist. Right? What happens to this data? This data is still occupying memory. Right? While your head is pointing to, let's say, if this was 1000, this is 2000, and this is 3000, while your head is okay now by pointing to 2000, head has not taken care of this particular memory being released. Just the pointer moved. This node is still there in memory. Right? Somebody has to free this node. So what we'll do is we'll say start temp. Start temp, please point to the head. Start temp, please point to the head. Head originally was 1000. So start temp, please point to the head. And then we will say that head arrow next, by which this becomes 200. Heads next is 2000. 2000, yes. So head equal to head arrow next means head becomes 2000. So here head becomes 2000. And temp is pointing to 1000. So temp still has the location of 1000. And then we will go and say that free this location. Free temp. So free this location. So then really this particular block will be freed, and that's what we are achieving from this particular syntax. What is the time complexity? There is no loop here, so we are doing, because from the beginning we don't need to do a loop, it will be an order of 1. The space complexity is also order of 1. Now if we had to delete from the end, let us see that also. So let's say that we have a list, and in that list we have to delete from the end, right? So the only point here is deletion is very easy, right? You can just move around the pointers and do it, but you have to be careful about memory, because deletion is always about memory. So head is, let's say, pointing here, and this is pointing here, and this is pointing here, and this is pointing nowhere, right? So that's the end of the list. Now delete from the end means I have to delete this, right? So what does that mean? That means, do I know this? Do I know, for example, head is at 1000, which means this is at 1000. which means this is at 2000, let's say, which means this is at 3000, let's say. So do I know that my end is at 3000? I don't know. How will I delete? Right? I have to free this. The pointer has to be made null here. So here I have to make it null. So this line will have to go away and I have to free this. That's all I have to do. Right? So if I do that, in order to do that, I have to reach to this node. Right? I have to reach to this node means from 1000 I have to traverse and come here. And how will I reach to this node? How will I reach to this node? In order to reach to this node, I will have to check whether wherever I am, when I'm traversing, I've put it inside temp. By now you should know it. Right? So wherever I am, if I'm here, right, if my temp is pointing here, is my temp next, arrow next is equal to null. That means my temp next, if temp is pointing here, then this next is pointing here. Right? If this next is pointing here, this next pointing to another node, no, this is null. Right? So temp arrow next equal to null means I will stop here. Right? So that's where we will start the loop. So let us see the code in action. Let us start clearing this out, right, and make you understand how this is going to behave. So this is the node, last node, and we will just delete these lines just to make sure you understand. This is the starting point and this is my 3000. So head equal to null, return, nothing to delete, understandable. If head next is equal to null, and this is the first case, right, this is the one element case. So that one element case is also specially handled here. We will come to this statement, right? Just be with me, we will come to this statement. Let's see the other part of it. Now what we have done is we have created a temp here and we have assigned it to head. So now we have 1000 here. Why? Because we want to use temp to loop, right? We cannot change head. Head, I said, is very sensitive, don't change head. We will just take temp and start changing temp. So temp, we will say that temp, you move yourself till temp next is not null, that I just now explained. So first time temp is at 1000, next to next, this is also not null because this is pointing here, right? So temp will move to temp arrow next. So temp will become 2000 because temp arrow next is 2000, right? So temp will become 2000. And the next time it runs, this next has a value, but does this next have a value? No. So temp's next is null. So it will stop. It will come out of the loop here. When it comes out of the loop, where is temp pointing? 2000. Right? Can I say that I will free wherever temp is pointing the next node of that? So can I say I will free temp arrow next? Right? Then this node is actually freed. Now all I need to do is make this pointer go away. Temp is at 2000, so I need to just make this as null. So that therefore we will say temp arrow next equal to null. And that's as easy as that. So we are just removing this pointer with this process. So that is for the element where you know that there is a necessity to probably do things when the position is not 1. If the position is 1, I mean if in case you just have one node and you want to delete it, right? So then we talked about this particular syntax, right? We will talk about this particular syntax now. So what happens if there is only one node? So let us delete this entire thing. So you just have this particular structure. Head arrow next is equal to null. So if I have to delete this, what do you think should happen? Head should become null. Right now head is at 1000. Head should become null and I have to free this. That's all I have to do. Right? So then my head arrow next is, and then how do I understand that this will have only one element? because my head is at 1000 and its next is null, its next is null. So head arrow next, if it is null, then just free head. Wherever head is pointing, free it. So fantastic, we have freed head. And what else we need to do? We need to change this to also null, right? So head equal to null, that's all we will do. So this is also very simple to understand. The time complexity here it will be an order of n, because here also you are using a loop which will be an order of n, and the space complexity here will be an order of 1. So just like your insert which is going to go to the end, we had an order of n. Here also we will actually have an order of n from a time complexity standpoint. Space will still be at order of 1. Now that takes care of delete from beginning, delete from end. There is one more delete. Typically we will use it for searching for a value and deleting that value, right? So again, let's take an example. So we will say that we have a 3 element list, right? So this head actually has, let's say, 1000, and this 1000 is having a data which is 75, which is pointing to, let's say, 77, and which is pointing to, let's say, 9, and which is pointing nowhere, and this is pointing here. So this is 1000, this is 2000, and this is 3000. Now we are saying delete 77. So if this value we are giving as 77 to be deleted, then what will happen, right? So what will happen is, if there is nothing to delete, means head is null, then we will just return like that. Otherwise what we'll say is, we'll take a temp as usual, and this is typically used for browsing, as you know by now. So temp should have head to start from the root node, and from temp what are we trying to search? We are saying temp, wherever you are pointing, what is your data? What is your data? Is your data equal to the value 77? 75 is there? No. Then what do? I will say head equal to temp arrow next. So what am I doing? I'm sorry, if it is equal, then we are going to delete. It's not there, right? It's not equal. So if my temp data is not equal to the value, then what I'm going to do? I'm going to just skip this entire position and go into a loop. So again, what are we achieving through this particular if? We are achieving the first case where we have only one element. So we will come to this case and explain. For now, let us explain these 3 element cases. And by now you should know that we have taken temp as a browsing element or a traversal element pointer, which I just now told you. So this, if it is pointing to 1000, how long should we traverse? We should traverse till temp becomes null or its value matches, right? So we should traverse till temp equal to null, and the value should also be checked. If the value is not matching, and temp is not null, keep on doing what? Keep on doing prev equal to temp and temp equal to temp arrow next. So we have taken one more pointer called prev, and I'll just now explain why. Right, so we have taken prev equal to temp. So prev equal to temp, that means the previous node is temp and temp becomes the next node by temp equal to temp arrow next. So temp now becomes equal to 2000. So temp will become equal to 2000. So what we have achieved through that, we are now pointing here, prev is pointing here. So wherever this node is, right, wherever this node is, the temp has moved to 2000 and previous is pointing to 1000, which is perfectly fine. We have not checked whether the temp data is 77. That will happen in the next iteration, right? The first iteration checked temp was here, right, 75. So 75 was checked, it was not matching. So temp moved forward, and whatever temp was pointing to, we stored that into previous, whatever temp was pointing to. So now this is the situation that is there. Now why is it necessary? We are trying to delete a value, right? And we will see why is it necessary. if you see the next time, let me go through the loop, then I will explain why is it necessary. So if you see the next time it runs, temp is not null. Yes, temp is 2000, 2000 is not null, but the temp arrow data is equal to the value. So we have reached our position, right? So we have reached our position means this will not fire, it will come out. And this is your state. This is your state of your temp and prev. So temp is pointing here, prev is pointing here, right? So that's what it is. Now why was this necessary? We are talking about delete. If this is deleted, then don't you think I need access to this next so that it can point here? So I need some prev, and that's why this prev. So you need two pointers, one pointer to point here which you will free, which is temp, one pointer to point to the previous which will actually take it here. And that's exactly what you did here. We will be doing, we'll say that if the prev, and what we'll do is the previous next is here, we will point it to the temp next is here, right? So the previous next is equal to the temp next. So as soon as we do that, the previous next starts pointing here, right? So the previous next will start pointing here, and when previous next starts pointing here, we should be in a position to delete this off. Where is this? This is in temp, so we'll free temp. So that's what we will do. That's why I need previous and next. And what is going to be the complexity? We have a loop here. You know by now, time complexity will be an order of n. Space complexity will be order of 1. Right? So this is your delete by value. And there are simple traversal operations that you should be aware of. It could be asked, and you would have understood it by now. If we have to traverse a list where we have a head, and the head is pointing to a node, and the node is pointing to the next node is pointing to the next node, and so on and so forth, right? If we have a head like that, then what we will say is that if we have to traverse through this list, then of course we have to take a temporary variable. The temporary variable will have to be assigned to head, whatever that head is. Let's say this head is at 1000, so the temporary variable will be at 1000. So, and we will run a loop. We will run a loop while temp is not equal to null. That is, we will go and inside this, and we will print the temp arrow data, and then we will say temp equal to temp arrow next. So this becomes 2000. Temp equal to temp arrow next. Next is pointing to 2000. So this becomes 2000 for us, and then we will print the data here. Then we'll say temp equal to temp arrow next. So this will become 3000, let's say, right? And then we will say that my next is already null, right? So if next is already null, we are not checking next as null. We are moving this from 3000 to the next, wherever we are, right? We are at 3000 at the last stage. We are at 3000. So temp arrow next is equal to 3000, and that is not equal to null, right? So but the next pointer is null, right? And because the next pointer is null, this loop is supposed to come out, right? So if this loop comes out, then we are done with the traversal, and we have reached a node which is null. So we have reached a node which is null, and hence we will stop the loop, right? We have been doing temp equal to temp arrow next, temp arrow next, temp arrow next, but at the end we have reached a node because temp arrow next is null. So we have reached a node which is null. Therefore temp not equal to null becomes false, loop exits, and we would have printed this by that time. So that's how your traversal happens. Time complexity, you know, because it's a loop, will have an order of n, and the space will be order of 1, right? So that's the traverse list. There is a search list, and you can understand that the same thing will happen, but all we need to do is, I'm not drawing it because it's going to be pretty much the same, or let me draw it, right? So let's say we have a head, and this head is pointing to a node which is having, let's say, 77, and this is at 1000, this is 75, this is at 2000, this is 3000, and this is at let's say 9, and I'm taking I'm saying that I want to search for an element with the value of 75. So I'm searching for an element with a value of 75. So what I'll do, I'll again take our friend, which is our temp pointer, and we will make it position to head. Head is pointing to 1000. So temp will also point to 1000. We'll take a position variable and we will put it at 1. So we are assuming that we will find it at position 1. So if you are assuming we'll find it at position 1, then the next part of the loop is taking temp's help and looping through till we find 75. So if we actually find 75, we will say that we have found it at the position wherever that position is. Otherwise we will and return. Otherwise what we'll do is we'll keep on moving temp. So temp will move to temp next, which is 2000. At 2000 we find, and of course we'll make the position moved. So position will also move to 2. Now we are at 2000 and the position points to 2, and we see that we have found this element, right? So we see we have found this element here. So if we have found this element here, then we are supposed to print what? That we have found it at position 2, and then we are supposed to return, and that's what this search list does. Time complexity is going to be order of n, and the space complexity will be order of 1, right? So that's on the search list, and that's pretty much that will be talked about in terms of the operations of a linked list, right? So let's start off with the application areas of linked list, and we will talk about stacks, and then we will talk about queue. Okay, so for the stack part, I hope you remember what is a stack, and just to recap that there is a top pointer, and the top keeps on pointing to the top of the stack, and we insert, or we call it as push. We push from the top of the stack, or we push to the top of the stack, and we also pop from the top of the stack. Now how can we create this stack structure using a linked list? We have done it using arrays, but you are no more children anymore. Long gone are the days for arrays. Now you have to start using linked list to create a stack, right? So we'll see how to create linked list now. We'll see how to create a stack using a linked list, right? So let me draw what I would want to achieve, and then we will talk about it. So let's say I want to achieve this in a stack. Let's say I want to achieve 75, 77, 9, and my top should start pointing to 9, so that my top is here, and then one more increment of the top will be the push operation that will have to be implemented. The pop operation will have to be implemented also, right? So typically we will be implementing push and pop using linked list, and that should be satisfying our basic requirements of stack operation. So data will be like this: struct node in data, struct node start next. All of them are the same, nothing changes, and we will have to maintain the top, just like we have the head for a linked list. In this case, top is the most important part of it. If we know top, we can push things to that pointer. If we know top, we can pop things from the pointer. So that's why we would need a top as a pointer, which will point to null for the time being. So let us assume that we have a top. We have a top which is pointing to which is pointing to null, right? So let us assume that we have this. Now if we are implementing the push operation, which is insert at beginning, then what do we have to do? The first thing we have to do is take our friend malloc's help, right? So we will take our friend malloc's help and say, malloc, please give me a memory. Malloc is happy. It says, I'm giving you a memory, and this is the memory that you wanted. And in that memory, I will say that I want to put 75, and that memory is, let's say, at an address of 1000, and I will say that okay, I will put that inside new node, right? So this is new node, that address where it's supposed to point, that fresh node is 1000, it starts pointing here, and in that I am saying that if I am unable to get a new node, that means there is a memory outage error. That means this malloc could not return me a valid address, so I'll print memory allocation failed. Otherwise I'll say wherever new node points, the data will be equal to 75, and the next will be equal to top. Next will be equal to top means next will be equal to run, right? So remember, we did insert at beginning. It's the same as that particular concept, right? So then we will and again you will ask that why top, why not null? And that's because the second time you do it, it has to move in, the top will have to move, and hence we will have to move according to the top, and hence we'll have to put it at the top, just like insert at beginning, the same thing. There's nothing different about it. Now if this is the case, now this top should not be any more null because we have one element in the stack. So the top should point to the current element, which is 75. So we should say, okay, enough is enough. You no more contain this null. You are supposed to contain what new node is pointing towards. So top will be equal to 1000, right? And then we just print that it is pointing here. So we have established this connection. So top is now pointing to here. So we are right now have created top, and we have created 75 as our first element of the stack. The code has ended, so this is no more there because it was a local variable. Top is a global variable, so it still will be there, right? Now next time we push 77, right, what will happen? Again, the fresh node will be allocated by malloc, and once malloc allocates the fresh node, we will use a new node to point to that fresh node, and let's say that is at 2000, and we are pointing here at 2000. Then we'll say new node, wherever you are pointing, I want that value to be 77. Where is this code? Here is the code. I want that value to be 77. And new node, wherever you are pointing, that next I want it to be at the top. Top is already pointing to here, so this will become 1000. So this now starts pointing here. And what do you think top should point? Top should point here, right? So top should not anymore point here because 77 is the top element now, and therefore top should start pointing here. And how will it be happening? We will say top equal to new node, right? So we'll say top equal to new node. New node has 2000, top is pointing 2000. We have achieved this structure now. Our top has moved from here to here. And see, it's exactly the same as insert at beginning, right? The same logic. Next time when it runs with 9, what will happen? Acha, by the way, next time means this is gone, no more there, right? And then we have the next time run. The next time, let me put it here. Next time it runs, it will be here, and this will be, let's say 1000, or rather 3000. We have a next. We will use new node to point to this 3000. So this is pointing here, and we are going to say that new node, wherever you have pointed, please insert the data of 9 there, and the new nodes next will be equal to top. Top was pointing, by the way, we didn't change top here, right? So we were pointed it to 2000. We forgot to change this value, so this is 2000. Now we are saying top new nodes next is equal to top. That means new nodes next will become equal to 2000. It will start pointing here, right? And of course you know that we should now not point the top here. Our new top is here. And how do we get new top as 3000? We will say top equal to new node. New node has 3000, so this becomes 3000, right? And that's all. So we have achieved 9. Our top has moved from here to here, right? And this is no more there, and therefore we achieved something where we can push elements and maintain a top pointer. That means we have achieved one operation using a linked list. The next operation we are going to consider are two operations primarily. One is on the pop part of it, and the other is on the peek part of it. Peek will be very simple once you understand pop. Now, if you remember, when we have this particular, we have inserted 75, 77 and 9, right? Our top is pointing here. All we are saying now is, if the top is null, then of course we have to handle the underflow case, which you have done in your arrays also. Now what we are doing is, we are saying that wherever top points, we will store that top. and let me write this for you. So top is now having, let me put the nodes first. These are the 3 nodes we are talking about. So one is having 9, the other is having 77, and the other is having 75. This is null. This is $2,000, and this is 3,000, and this is 2,000, and this is going to be 1,000. So this is our structure of this particular stack. Now we are trying to do pop. So we will take a temp. We'll take a temp that points to top, and what we'll do is we'll just say temp's data is what we have popped. Temp's data is 9. So we will say we have popped 9. So we will say we have popped 9 through this particular printf. And we will also say my top next is equal to this, because we have popped this means we have to remove this pointer and position this pointer here, right? So my top next is what? Top next is 2000, and that should be the value of the new top. Top next is 2000, that should be the value of the new top, right? So this becomes 2000. But still, if you see, pop means delete, so this should be deleted. So we have to free 100,000. Where is 1000? 1000 is here. So we will say free 10. So that's on the delete. So whatever you did in delete, whatever you learnt in delete, we are using the same things here. We are pushing the top to the new node or the next node, and we are deleting the previous node by calling free, and this temp is actually helping us do that. What is the order of this? The time complexity for this is going to be an order of 1, because we are deleting from the top. We have direct access to the top, therefore order of 1. The space complexity will also be order of 1. Right? Now, if we talk about the peak operation, then in the peak operation, all we need to do is we need to peak what point wherever top is pointing, right? So we just need to peak wherever top is pointing. So we just need to print the top arrow data. That's all. That's all we need to do. There is no loop here. Time complexity will also be order of 1. Space complexity will also be order of 1. Nothing more to do fancy about it. We are just printing the top data, right? So top will always point to the top data, and we will say top data is empty. Of course, is empty is top equal to null. I'm sure there's nothing much to explain about it. So that's on the usage of stack using a linked list. Now, if that is possible, then queue is also possible. So how do we do a queue? Let's figure that out. For a queue, you know what are the 2 pointers you need. You need the front, which is null, and you need a rear, which is also null, right? And how will the queue look like? Right? So if I have a queue like this, and I will be inserting from the rear. So let's say I have inserted 75, 77 and 9, right, into this queue, and this is my front, this is my rear. Now we are talking about these 2 variables. We have defined this here, and we are talking about an NQ operation. So we are if we are talking about an NQ operation, let us go through that NQ operation now. So what we'll say is that the first NQ was 75. So if we have 75 as an NQ, then this 75, to store 75, we will ask malloc, give me space. Malloc will give us space. We will store that address in new node. So new node has 1000. Malloc gave us space. So new node has 1000. If the new node is failing, we will say some error. New node's data will be equal to 75, and new node's next will be equal to null. Right? Because that's all that we need to do. All we need to do is front, we will need to position, and rear also we will need to position to this particular new node. Now, if we have a new node created, then if for the first time the queue is empty, both front and rear are null. If front and rear are null, which is the case in our case, then this code will fire. So as I said, front will need to position here, rear will also need to be positioned here, right? So front equal to rear equal to new node. So all inside front and rear we will have 1000. Why 1000? Because this was returned by malloc as 1000. Front and rear will become 1000. Now front and rear has become 1000, which means that we have now successfully created our first element in the queue, and it is returning out, which means this particular variable has gone out of scope, right? And these two variables are global variables, so they will stay. Now we are now enqueuing 77 rather, right? So when we enqueue 77, malloc will give us a space. When malloc gives us a space for 77, we will say that there will be a new node, and this new node will have the new address of the new node, and 77 should be having null here. Why? Just this line, right? 77 will have null here. The queue is not empty, so now we are here. Queue is not empty. So what should happen? Our rear should move forward. In a queue, remember, when we enqueue, the rear move forwards, the front stays wherever it is. So our rear should move forward, so this rear should not point here. So the rear should point here. How will the rear point to 2000? The rear will point to new node, or rear's value will be new node rather. Then the rear next, rear is pointing to new node. Before pointing this particular thing, we will have to adjust the next pointer of rear. Right now, because we can't lose this 1000, right? Before changing this 1000, we need to have access to this 1000 to change this pointer like this. So we need to hold this 1000 before we change it to 2000, and that's why this statement has to come first. So we will change, we'll take this 1000, and then what we'll do? We'll just remove this null. So we'll say rear, wherever you are pointing, that next has to become equal to the new node. So rear, wherever you are pointing, that next has to become equal to the new node. So this will become new node, right? And now we can change this rear to new node, so that rear, this connection gets established, and therefore this becomes 2000, and that's what we will do. Now if we have another element to be enqueued, then let's see how that happens. We have another element which is 9. So if we have to enqueue 9, then we will create this memory. Malloc will happily create it for us. New node will start pointing to 3000, right? And this 3000 is this new node for us, which is 9, and we will have null. And then what we will do? We will say my rear, wherever you are pointing, that next, rear is pointing to 2000, that next should point to 3000. So we will say go away null, and you become 3000. And rear, you cannot point to 2000 now, you will now need to point to 3000, right? So you will now need to point to 3000. You have moved to 3000 because new node has 3000. So rear equal to new node will make rear point here. So this structure or this pointer will cease to exist. So now your front is here, rear is there, 75, 77, 9, you have achieved what you wanted to achieve, this structure, and hence your enqueue operation is working perfectly fine. So if enqueue is working perfectly fine, then let me draw that enqueue for you. So for that, we will again draw front. Front is pointing to 1000, and let me draw the nodes. This is 1000, it has 75, which is pointing further to 2000. At 2000, this is pointing to or having 77, and it is pointing to 3000. At 3000, the node that we have is 9, and this is pointing to null. And my rear is pointing to 3000, So front points here, rear points here. We have created a queue using linked list and the enqueue operations that we discussed in the last slide. So now in the dequeue operations, what is going to happen? Our front is null, and of course if front is null, then it's an empty queue. So we'll have to check the underflow case. After that, what we are going to do is dequeue always happens from where? Dequeue will always happen from the front, right? So we will say that, okay, we will take a node which is a temp node, and we will make it equal to front, and we will use this temp node to dequeue. So we'll say dequeue temp arrow data. So we'll say dequeue temp arrow data, right? Now if temp arrow data is gone, right, there are 2-3 cases that will exist, or rather there are 2 cases. If temp arrow next is gone, then what should happen? Our front should change this pointer and point here, and we should be able to delete this, right? So to free that, we know what to do. We'll say free, because 1000 is pointing here, so we will clearly say free temp, and that's what we have done here, free temp, to actually delete it. But we also have to make front point to temp arrow next, or front, wherever it is pointing, front arrow next. So front has to point to front arrow next. Front was pointing here, so front was pointing here, front's next is 2000, so front will become 2000. So now front has 2000 because front's next is 2000, which we are inserting into front, and therefore this connection ceases to exist and this new connection gets created, right? So this connection ceases to exist and this new connection gets created, and all we need to do is now delete this element. Deleting this element will automatically delete this connection also, and that we will achieve through free temp. That's what we have done here. So that's the algorithm for your dequeue, right? There is no loop here, so this time complexity for this will be order of 1, space will also be order of 1. Peak, and again it's going to be very simple. You are supposed to peak, and by the way, if the queue is empty, that is by going to front arrow next, because if you delete the next element, then this is gone, and then when you are starting to delete this 3000 element, the next is null. So therefore your front will become null. Then if front becomes null, make rear also null. That's the additional condition that you will have to put, right? That's something that you also put in dequeue operations using arrays. Peak, very simple. You check for front becoming null, which is the queue is empty case. Otherwise, wherever front is pointing, peak will always peak that element. So front arrow data, nothing else. So that's all you do. Empty check, if front is null, obviously it is empty, right? You can also say front equal to rear equal to null. It's more safer. You can do that also. So that's on the queue part of the application of the linked list. And that's pretty much what I had to cover for this lecture. We'll take a short break. Let's take a quick drinks break or whatever you want. Let's come back in another 2-3 minutes and see what we can do for solving the most common problems that are typically asked, right? We'll come back. Okay, welcome back, and let's complete the understanding of the areas that we had discussed around linked list and the applications of linked list around the stacks and queues in terms of the common questions that are getting asked. So the first question is going to be pretty simple. What is the time complexity to insert an element at the front of the linked list, right? If we are inserting an element at the front of a linked list when the head pointer is already given, right? So if we know the head pointer, so head is pointing to a element and this element is proposed pointing to this element. Now if we have to insert an element at the front, means we have to insert it here and head should start pointing here. What do you think should happen? We just need to create a node like this, right? So we just need to create a node like this, number one. Number two, we will have to position this here, right? So whatever head is pointing to, we will say, wherever head is pointing to, we will say this new node point there, and then we will say head start pointing to this new node, and you no more point to this way. What did we do? We did two pointer operations and one node creation. What is the complexity of that? Order of 1. Right, so that's all. That is the answer to this question. And linked list, typically, because it is a linear data structure, right, so it should not be suitable for any division and conquer kind of an algorithm. It, as I explained in the first slide, that we are talking about linked list where it has to be a sequential access. You have to go from one node to the next, to the next, to the next, to the next. You cannot skip nodes, and divide and conquer will typically divide it, and we have to skip nodes, and therefore we cannot basically implement binary search using linked list. And the next question is also around the same thing. We cannot use binary search using linked list, right? So that's what these two questions typically talk about. Next, it's asking us to create a linear linked list with n nodes. It's simple. You just have to have an additional loop for n at the outside. So this is that additional loop for n at the outside. So every time you will actually create a node, you will need to check whether I have created that many number of nodes. This loop is just to justify that, right? So the rest of the stuff is going to be simple. It's the same thing that you are doing. You are creating initially your head will be null, right? And you will be creating a new node. This new node will be created. So you will follow, let's say, insert at beginning kind of a concept, or insert at end kind of a concept, whatever you follow. This head, which is pointing to null, signifies that the list is empty, and therefore when you ask malloc to create a node for you, this node will, let's say, have 77. You will have a new node pointer which will point to this 77, which is, let's say, at 1000 address. And if the head was null, then you will have to make head equal to the new node, because head will therefore point to 1000. So head will become pointing to here, and that creates your linked list, right? And then later on, when you keep on adjusting, if head is not null, that is in the second instance, what you have to do, you have to create a new node again through malloc's help. Your new node will point there, right? And what you'll have to do, put the element there, which is, let's say, 75, and then what you need to do is put a null here, in this case the last element, right? And all you need to do is that you will have to traverse through a loop. If you remember the insert at beginning code, the same code, you'll have to traverse through a loop by taking a temp, right? By taking a temp which is pointing to your 1000, that is your head, and you'll have to traverse there and stop at the node just before the last node, or rather you have to stop at the last node, so that you get an access to the last node, and you can change the pointer of the last node to now point to 2000. We have discussed it. It's the same code, same algorithm. The same thing is written here. All that is extra is this particular loop, which you will have to run n number of times in order to create a linked list for n nodes. So that's on this particular question. The next question is append a new node after a specified node, right? So after a specified node means that we have done what? Insert. We have done insert at position. What this is saying is insert after value. That is what this is saying. We have not done this. We have done delete at the value, right? And now we are going to see how to do insert after value. So that's again going to be simple enough. So if we actually say that we have a head which is pointing at let's say 1000, and we have 1000, we have 2000, and we have 3000. So this is my 1000, this is my 2000, this is my 3000, and this is pointing to null. This has 9, this has 3000, this has 77, this has 75, pointing to 2000, and this is my linked list. In this linked list, I want to insert a new node after a specified node after 77, if that is a requirement, right? And then what we'll do, we'll take a pointer, because we have to go till here, right? After means we will have to create a new node like this, which is, let's say, at 4000, and then we have to say that we have to, instead of this pointing here, we have to say that you have to point here and you have to point here. So that's all we have to do. And of course we'll have to, and when we say this points here, then this will be automatically removed, right? And this is the new node. So the new node will have some value, let's say 99, and this new node value 99 the next part of it we are adjusting with this pointer. This is what we have to do. So what we'll do is we will create a new node, and that new node will have 4000. So this is my new node, right? So that new node which is having 4000, but first we'll have to traverse, right? So we'll have to go through this 1000, and we will go till what? We will go till my element is not found. So if my element is found, I will exit. So see, here is the loop. If the element is not found, go on and increase PTR next. So this PTR is your temp that we have been using. So for now, let us assume that PTR is equal to my head, right? And then head through PTR, we were navigating this particular linked list till we actually got a match of our 77. As soon as we got a match of 77, our PTR is therefore pointing to 2000, right? Because it exited here, so it should point to, it exited here, so it should point to 2000. So when it exits there and it points to 2000, then we now have a scope to say that my PTR, wherever it is pointing, that next should be the address of the new node. So we should be saying new node next, your address, new node is pointing here, its next is PTR wherever it is pointing, that is 2000's next, which is 3000. So therefore now this connection gets established, and then we should say that PTR's next, PTR is pointing to here, so that PTR, that next, this 3000 is no more valid, right? So this 3000 should be replaced to what? This 3000 should be replaced to the address of the new node. In fact, I was wrong in saying this establishes this. I should have said that when we said new nodes next is equal to PTR's next, and we put 3000 here, it is actually establishing this connection, right? And by saying that my PTR's next is equal to my new node, my PTR's next is equal to my new node, I am establishing this connection. So this now becomes 4000, right? And that's all that algorithm is. So all you need to remember is create a placeholder. First write the array like this, right? I hope you can do that. First write the array like this. First write the array like this. Whatever is the existing array, just assume certain things, write the array, and then move on. What will move on? We'll say that, okay, new node is this is an insert operation, right? So this is after a specified node. So do a browse. After means after this we have to, so we have to stop here. So understand where you have to stop. You have to stop here. And then wherever we stopped, right, we had that inside a temporary variable, not head. Mind it, don't move head. We had that inside a temporary variable. So if we have this inside a temporary variable, then that temporary variable's next is where it was pointing. This should start pointing there. So that next becomes this. And this should no more point there. So this should point here. So that pointer's next should be the new node. So it's as simple to imagine. If you know what you are doing, right, if you know this diagram, the rest of the code should be very easy for you to actually achieve. And I hope it is like that. So that's on this particular portion. Next question that comes is write an algorithm to delete the last node of a linked list. We have done this here where we said that delete from end, right? If you remember, this is delete value, and this is the delete from end. So we have done this. This is the algorithm, right? So just refer back to the lecture. You will get an answer to that. The next part of this is I think around polynomials. Okay, we have a middle of a linked list, right? So we have to insert an element to the middle of a linked list. Now let us take a list like this. In fact, let me draw the list. So we have one element here, one element here, one element here, one element here, and one more element here. right? So we know this is the middle of the linked list, right? And we want to insert the element in the middle of a linked list, but we don't know what is the middle value. The problem is that we don't know what is the middle value. What is this node? I have to insert. That means I have to create a node like this. You know by now, a new node has to be created. This pointer will have to go away. We have to create a pointer here, and we have to create a pointer here. That is all you have to do. 2 pointer operations, 1 insertion, right? So that's what you have to do. For that, you need access to this particular node. So you need a pointer to this particular node. And you don't know the pointer. What is the middle of a list? How will you know? You don't know the total size of this list. So what will you do? There is a head, yes, which points here. So all you need to do is take 2 pointers. One, call it as a slow pointer, and this, the value, put it as head, whatever that value of head is, right? So put it at the value of head. And you take a fast pointer and put it at the value of head also. Now all you need to do is run a loop and say that slow, please go to the next pointer. So slow was pointing here. So slow was pointing here. Fast was also pointing here because it was pointing to head, right? So now say slow, move on to the next. So slow's next is equal to the new slow. So slow is equal to slow's next. Say that. So if you say that, then slow will go here. Slow is no more here. And you say fast, you go to the next. That means fast will go here. So fast, you go to fast next. So fast has gone here. So basically you are saying that fast move 2 steps, slow move 1 step, right? So this now goes to the if I just name this as the first element, second element, third element, fourth element, fifth element, then that slow is now pointing to the second element, and fast is now pointing to the third element. And then again the loop goes on. When does the loop stop? When either the fast is null or the fast next is null. Because you are moving 2 times, you have to also check the fast next to be null. There is no point moving to next when next is actually null, right? So therefore what you will do is you will go there and then you will say that move slow by 1 pointer. So slow will go to slow next. So slow starts pointing here, and move fast by 2 pointers. Next. So next to next, right? So next to next means here. Wherever this is pointing, it will move there. So therefore my fast goes here, my slow is here, right? And this therefore now points to 3, and this therefore now points to 5. So now if I do this loop check, then my fast next is null. My fast next is null, right? And therefore it will stop. Now I am in a position to say that my middle is the value of slow. We are at the third position, and the third position will be the middle. So now we got the address of this particular element in the slow pointer. Once you get the address of the element in the slow pointer, the rest of the things you have already done many a times. You have to create a new node, right? And that new node will be pointing here. And all you need to do is say that your next, new node's next, will be the slow pointer's next. Slow pointer was pointing here, so the next is pointing here, so the new node's next should point here. So you are establishing this connection. And then you are going to say that slow's next, slow is pointing here, so this next should not point here. This next should start pointing to the new node. So slow's next should point to the new node, and then you will stop. But this particular thing you have done many a times. I have explained to you many a times in this session. So I hope this you can write blindly. Only concept here is slow and fast pointer to reach to the middle of the list, right? So I hope you have understood that. This we have covered. I will not cover this. It's there. You can offline read it. linked list and linear array, we have discussed what are the differences. Now, the interesting question is, how can you represent this using a linked list? This is a polynomial, and you see that this is sorted in the descending order of its degree. So in order to represent this as a linked list, we will say that this particular element, we can reproduce this particular 6x to the power 3 if we know what all this contains. What does it contains? It contains a coefficient, and it contains what? It contains a degree, or let's say it contains a power. Let's call this as power, right? So if we can store the power and the coefficient inside something, and then link it to the next element, and then link it to the next element, and then link it to the next element, then we can actually reproduce something called as a polynomial, or store something as a polynomial. So what should our structure look like? So we have to write that our structure will look like this. Struct node, we will store what? What is the coefficient? It's going to be an integer. So we will say integer coefficient, right? And what will the next thing need to be stored? We have to store the power. So we will say integer power. What next we have to store? We have to store the next pointer, right? So we will say struct node star next. So it's not always that you have to have one data. There can be multiple of data, and that data can be of multiple types. So what I'm saying is, here you can have many data, and these data can be of multiple types. All you need to imagine is everything here is one block which is called data, and you have one block which is the next pointer. That's all the linked list is all about, right? Internally it may be so much of data. So you have coefficient and power here. Now if I start creating a node out of this, or if I start making the first element will look like what? I will have 6 as my coefficient, I will have 3 as my power, and I will have the next element's address as my next element, and my current element address will be 2000, and I will have my head which is pointing to my 1000. So head is pointing here, and this is a pointer, and therefore I can now create the next element. What is my next element? My next element is 4x square. Now should I write 4x square? No, I should write minus 4 as the coefficient, right? Because when we start reproducing or start traversing this list and try to create this polynomial, we should be able to create the polynomial with a negative sign wherever required, and that negative sign will come from here. So we will store minus 4 here, and we will store 2 as the power, and we will store 3000 as the next address, assuming that the next address is created at 3000, right? So in that 3000 address we will store minus 2 again. X has a power of 1, so we will store 1, and then we will store 4000, and then the last term we will store is 10, and this is at 4000. And when we store this 10, right, what is going to be my power? My power is anything to the power 0 is 1, so my power is 0. X to the power 0, 10x to the power 0. This can be written as what? 10x to the power 0. Anything to the power of 0 is 1. So 10x to the power 0 will be also 1, and that will make no difference, and the next will be null. So this is how you have to write this answer, that we have to first create a node, a structure which will look like this, so that we can create the individual nodes of this particular list, and therefore we can traverse this node and create this polynomial. Can we do the traversal and see? So we have head, and when we start traversing we can get into 6. So when we get 6, we know we have created this, we know 6 is the coefficient. So can I say I will printf 6, right? Or I will printf coefficient. I will printf the coefficient, right? So the value of the coefficient. So let's say I will say printf %d, the value of the coefficient, right? Or we can simply say, because we will be traversing the list, something will be inside temp, right? There will be a temp, so temp arrow coefficient, right? Traversal means what? There should be a temp which will point to head, right? And using this we will be moving temp equal to temp arrow next inside a loop, you know by now. And then every time we move the loop, we will do a printf. Inside this loop, we will do the printf. Right, that temp arrow coefficient. So temp arrow coefficient is 6. Right, after that we have to say x. So after this I can say x. So I will start utilizing this section and say x to the power, because I can't write degree superfix, I will use the exponent sign, to the power of what, I don't know that. So I'll say to the power of in fact I will also need to, let me rephrase or rewrite this. %d, then we will say x to the power another %d, right? And then we will say temp arrow coefficient and temp arrow power. If we do that, don't you think temp arrow coefficient will be 6, then it will come x to the power of power, so which is x to the power of 3. Then minus 4 means minus 4 x arrow 2, then minus 2 x arrow 1, then plus 10 x arrow 0. This will be printed. Right, here we will have the exponent symbols. We will have the exponent symbols. So x arrow 1 plus 10 x arrow 0. You can make it more intelligent by putting an if else and saying that if it is x arrow 0, then no need to print it like that. That we can do. So ultimately the bottom line is that could we store a polynomial inside a linked list and then reproduce the polynomial? We could, right? So this is how we have reproduced the polynomial. We have gone through the linked list and we have printed the polynomial the way it is supposed to be printed. The next example is a variation of this. Show how the following polynomial can be represented using a linked list, and you can see there are two kinds of powers here. So we'll take the same thing, struct. First of all, validate whether these are in descending order, and I'll tell you why in the next example. Right, so they are in descending order of powers. There is nothing wrong with it. In fact, here you don't need to, because there are multiple powers. You can't validate both the powers, right? At least x is in descending order, so that is okay. So struct node, and then you will say that int coefficient, and then you should be having int p1 for the first power and int p2 for y's power. You can write any kind of variable names, and that's the structure that you have to write. Please write this as how they said, how the following polynomial. So you'll say we'll create a node like this, and please explain what this will point to, what this will point to, what this will point to, right? And after that you say that this is how it will look like in terms of the map of the linked list. So you'll say that I will have 7 here as my coefficient, I will have 2 as x's power p1, and I'll have 2 as y's power, and then I will be starting to point to 2000. So there will be a head which will be like this, and it will point here. We could be very professional and say, okay, no more heads, it is a polynomial, so let us call it as poly, right? So it will point to this, which is at 1000, and then we will say 7 to 2000. This will go to minus 4, 2 and 1, and this will go to 3000, and then we will say plus 5, 1 and 2, and this will go to 3000, and then we will say this will go to minus 2, 0 and 0, and this will become null, right? So this is how you will draw it, and then say that this is how it is getting represented, right? And don't need to represent back the printfs that I told you unless they ask for it, but the printf I showed you just to make sure that you understand why we are doing it. We are storing it as a polynomial here so that using a loop we can further retrieve and do some kind of mathematics. What kind of mathematics? Let us see in the next example. Show how the linked list can be used to add two polynomials. So these are my two polynomials that are given to us. Notice that one of the polynomials has a variable raised to the power of 4, and the other one has a variable raised to the power of 3, right? So what we'll do is assume that we have created two polynomials, one called poly1, right, which is pointing to the element which is 5 and 4, and this is pointing to 5 and 3, and this is pointing to 10 and 2, and this is pointing to 8 and 1, and this is pointing to 3, this is pointing to 3 and null, right? So this is my first polynomial. My second polynomial, let's call it as poly2, and my second polynomial is looking like this, which is having 3 3, and then this is having 2 2, then this is having 7 1, and then this is having 8 0. I'm sorry, this should have been 0. I'm not showing the address of the next anyways. I'm utilizing the arrow for that, so inside it I'm showing only the data portion. So this should have been 0, right? So poly is now pointing here. Now we will say that we'll run a loop and we will check whether we can add these two polynomials only if their coefficients are the same. So if this coefficient is same with this coefficient, we can add it. But our pointer poly is pointing to the first element, and the first element here, which does not exist for that particular element combination, is a 0 with a 0. 0 is basically the element that exists here, right? We can assume that 0 is an element with a power of 4, with a power of 4 that exists here, right? So because we have to make these two the same, right? So I'm asking you to assume, you don't have to write any code for that. Just assume that there is an element like this here. If you assume an element like this which exists here, then all you need to do is that while both the powers are not null, you are supposed to check whether the power, in this case it is called as exponent, right? But we'll stick to our power concept, right? So if the power of our polynomial 1, if the power of polynomial 1 wherever it points to, so if polynomial 1's power, that is our case 1, if polynomial 1's power is greater than polynomial 2's power, if polynomial 1's power is greater than polynomial 2's power, then we need to create a resultant polynomial which will add 5 with 0 and keep 4 as same. So evidently, if I talk about the resultant polynomial, then this resultant polynomial will therefore have 5, 4 as its first element. Resultant means the sum of these two polynomials. So what we'll say is create or insert into that resultant polynomial. What do we insert? What is the node? The node is 5 and 4. Where is 5 going to come from? Polynomial 1's 5, right? So insert what? Polynomial 1's coefficient, right? Polynomial 1's coefficient is as if getting added with an imaginary 0, right? No need to do that in code, and the power will still be 4. So the power will be polynomial 1's power. So that's all you will say. Insert this particular element in my result, and this will create this node for you. Else, what will happen? Else, polynomial 1, the other way around, polynomial 1's power will be less than polynomial 2's power. And if that happens, when will that happen? It will not happen here anyways. Polynomial 1's power will never, and by the way, we missed one step. Let me do that step. So polynomial 1, the coefficient of polynomial 1 was taken forward into result. Therefore, polynomial 1 can now safely move here, right? So polynomial 1 has to move here. So this will cease to exist. So what we'll say? We will say that polynomial 1 is equal to polynomial 1 arrow next. So we will safely move polynomial 1 here. So now polynomial 1 is pointing to a degree of 3. Polynomial 2 is also pointing to a degree of 3 because this was a non-existent node. Na? So we had made sure you assumed it. It's non-existent. But polynomial 1 and polynomial 2 both are pointing to a degree of 3. The degrees are matching. Now we can add them. Right? And suppose it was the other way around, that this polynomial 1, the power of this polynomial 1 was less than the power of this polynomial 2, which will not happen in our case. But suppose because in this case polynomial 1 is this, polynomial 2 is this, never do we see the powers of polynomial 1 less than the powers of polynomial 2, right? It would have been the case if this was reversed, right? If this is reversed, then we'll have to make a case for that. Suppose that came, then what would happen? Same thing, you will insert what? You will insert polynomial 2's coefficient, right? And polynomial 2's power. And then you would have moved polynomial 2 to polynomial 2 arrow next. That is what you would have done, right? And the third condition is when we are right now here, right? When both the powers are matching, both the powers are matching. If both the powers are matching, then all we need to do is insert what? Polynomial 1, the coefficient of polynomial 1, we will need to add it with the coefficient of polynomial 2. And the value of degree we will give as any one of them. Polynomial 1 arrow power. That's it. And of course, we'll have to do a polynomial 1 move next into polynomial 1 dot next, and polynomial 2 move next, which is polynomial 2 is equal to polynomial 2 not next. I hope you can understand I'm talking about these two statements. So we'll have to do this statement and we'll also have to do this statement here. So what we did is we added the two coefficients, we kept the power any one of them, right? So this got added. So now what we have is 5 will get added to 3. So we will get a result which will have 5 plus 3, which is 8, and then 3. Then we will have 10 plus 2, which is 12, 2. Then we will have 8 plus 7, which is 15, and 1. And then we will have 3 plus 8, which is 11, 0. So that is going to be the resultant once all of this is executed. And this is the same thing that is written here, right? So I hope this particular problem is understandable. This was a tricky problem, but I hope I could make you understand how to probably approach it in an easy manner. With that, I think we don't have any further questions. Yes. So with that, we come to the end of this particular lecture on linked list. Circular and double linked list is something we'll cover in the next class. Till that time, keep studying, and as I said in the last lecture also, exams might be near depending on when you are seeing this. So keep studying, keep approaching new algorithms, keep understanding the algorithms, don't mug up the algorithms, and make sure that you understand so that you can reproduce it in English. Till the time we meet next, have a nice day ahead. Thank you so much.